Hello and welcome back to Creo with Chris. In the previous lesson, we designed and built a fully parametric straight bevel gear system from scratch. We explored how bevel gears can be used to transform motion and power between intersecting shafts. We created fully parametric gear models using parameters, relations, and equations, and finally assembled and animated the completed gear system inside Creo Parametric. In this lesson, we're going to build upon those foundations and tackle an even more advanced gear type, the spiral bevel gear. At first glance, as you can see, a spiral bevel gear may look very similar to the straight bevel gear system we created previously. Both gear types are used to transmit power between intersecting shafts, most commonly at 90 degrees, and both rely upon many of the same fundamental geometric relationships, including pitch cone geometry, cone distance, pressure angle, and gear ratio, and so on. However, spiral bevel gears introduce an additional level of complexity because the teeth are curved rather than straight, as you can see. This seemingly small change provides several important advantages. Spiral bevel gears generally operate more smoothly, they produce less noise and vibration, they allow greater tooth contact during operation and are capable of transmitting higher loads than equivalent straight bevel gears. Because of these advantages, they are commonly found in automotive differentials, aerospace systems, industrial gearboxes, robotics, and other high-performance power transmission applications. As a result, spiral bevel gears are often preferred whenever smooth operation, higher load capacity, and quieter performance are important design requirements. From a modelling perspective, many of the early stages of this project will feel familiar. We'll still begin by defining the fundamental bevel gear geometry using engineering calculations and relations, and we'll still use a fully parametric workflow to drive the design. However, once we begin creating the tooth geometry, we'll introduce a curved tooth path controlled by a cutter radius and a spiral angle. This additional geometry creates a much more complex tooth form and requires several new modelling techniques compared to the straight bevel gear project. Another important difference in this lesson is that we'll be using what is known as an unequal addendum system. In the straight bevel gear lesson, we used an equal addendum system, where both gears shared the same addendum and dedendum values. This simplified the calculations and provided an excellent foundation for understanding bevel gear geometry. For this project, however, we'll be using a more realistic approach commonly associated with the Gleason system. In an unequal addendum system, the smaller pinion gear receives a larger addendum and a smaller dedendum, while the larger gear receives a smaller addendum and a larger dedendum. Although the overall tooth depth remains the same for both gears, this redistribution of material improves tooth strength and helps optimize the meshing behavior between the pinion and gear. It also reduces the likelihood of undercutting on the smaller gear, which is often subjected to higher stresses. Don't worry if this sounds complicated at first. The spreadsheet and relations provided with this lesson will handle the calculations automatically, and throughout the lesson I'll explain any reasoning behind the key dimensions as we progress. As with the previous gear projects, this lesson includes the downloadable calculator spreadsheet that we'll use to generate all of the critical dimensions required to build the gear pair. The spreadsheet also includes copy-ready Creo relations that can be used directly within your own models. By the end of this lesson, you'll have built a fully parametric spiral bevel gear system from scratch, created both mating gears, assembled the final mechanism, and produced a working animated gear system inside Creo Parametric. Let's begin by taking a look at the calculator spreadsheet and exploring the engineering relationships that define the geometry of our spiral bevel gear system. Much like the straight bevel gear project, we're designing a complete gear system rather than a single component in isolation. The dimensions of gear 1 directly influence the dimensions of gear 2 and vice versa. The spreadsheet allows us to define a relatively small number of design inputs and automatically calculate the remaining dimensions required to build the entire gear system. As ever, first we have the shaft angle, which defines the angle between the two gear shafts. For this project, we'll again be using a 90-degree shaft arrangement. Next, we have the module, which defines the overall size of the gear teeth and must be shared between both gears. We then have the pressure angle and the mean spiral angle. The pressure angle controls how force is transmitted between the teeth, while the mean spiral angle controls the curvature of the tooth path and has a significant influence on how the gear behaves. Finally, we have the gear teeth for gear 1 and gear 2. Again, for the purpose of this lesson, we're choosing 40 teeth for the crown gear and 20 teeth for the pinion gear, and this creates a gear ratio of 2:1. From these values, the spreadsheet automatically calculates the reference diameters, pitch cone angles, cone distance, face width, addendum values, tip diameters, root diameters, and the various dimensions required to generate the spiral tooth geometry. You'll also notice the cutter radius calculations. This is one of the new parameters introduced in this lesson and is used to define the curved path that generates the spiral tooth form. Unlike the straight bevel gear, where the teeth follow a straight path, the spiral bevel gear requires us to define a curved trajectory that controls the sweep of each tooth across the gear face. If we now go over to the Relations tab, you'll notice that we actually have two different sets of gear relations. One for if we choose the unequal addendum relations, and one if we choose the equal addendum relations. If we go into the inputs here, there's a drop-down menu, and you can switch between equal addendum, which will affect the maths in the calculations here, or we can choose unequal addendum here. So you can create the spiral bevel gear with equal addendum formulae, as with the spur gears and straight tooth bevel gear, but it is more correct to use the unequal addendum for building a spiral bevel gear calculator, but you can use either. So when you build your own parts, make sure you are copying in the correct relations for your model, depending on which addendum relationship you want to use, equal or unequal. In this lesson, we are going to be using the unequal. One thing I'd encourage you to do at the end of this lesson is experiment with a spreadsheet, try changing the module's spiral angle or tooth count and observe how the calculated dimensions update. Bring this through to the models you do, see where the model fails, see where it doesn't. But through this observation, this is one of the best ways to develop an intuitive understanding of how spiral bevel gear geometry behaves. After this, I'm just going to jump forward through to some of the sketch references here. So again, we have the same initial sketch reference as we had for the straight bevel gear, as well as the reference circles here, but we have sketch reference gear 1, sketch reference gear 2 that provides you with an overview of how we build in the spiral path that will form the trajectory of the teeth. Gear 1 for the pinion, gear 2 the crown. Okay. So now that we understand the key inputs and outputs that define the gear system, let's move into Creo Parametric and begin building the first gear. Okay, let's get started with building the spiral bevel gear system. We're going to be starting with gear 1. So let's create a new part, get rid of the default template. Let's call this spiral bevel gear SVG. Pinion gear 1 L for lesson. Okay. We don't need to save that. No. All right. So I'm going to be using millimeters, kilograms, seconds. You have yes. Okay. Let's bring actually all of these back. Okay. So how do we start? Well, first off, let's get back into the calculator. We want 40 teeth, 20 teeth, that stays 35, that's the commercial standard. Pressure angle module, yeah, that's all fine. We want to make sure we're using the unequal addendum, yes. Okay. So first off, relations and parameters. So make sure we get over to the Creo Relations tab, and we're going to be putting these in first as our parameters. So model intent, parameters, On default, yes, plus. So the first one is shaft angle, 90. This is for the intersecting axes of the bevel gear system. Next is the module, which is 3. Next, the pressure angle, which is 20. The mean spiral angle, which we'll be using 35. And then we've got Z1, 20. And we've got Z2, 40, which are the respective gear teeth for gear 1 and gear 2. Okay, parameters set. Now we need our relations. So again, basically what I'm going to do here, these have been split up to sort of show you the calculations for each different section. So we've got reference diameters, pitch cone geometry, the face width, the unequal addendum tooth height as opposed to the equal addendum tooth height, which follows the standard profile that we'll have seen in previous builds, as opposed to the slightly more complex maths in calculating the difference in addendums and addendums in the unequal addendum tooth height system. Clearance rates, angles, diameters, and so on and so forth. We're basically just going to, from reference diameters, making sure we're in the right relations panel that we want, scroll down all the way to the bottom before we get to the involute equation, and we're going to copy this in by Control-C. Back to relations, Control-V, verify, and press OK. And now you'll see we have, there's so much more going on with a spiral bevel gear than even a straight tooth bevel gear. And you can see all the maths extending below here that we'll be getting to eventually. Not all of them, but some of them. Okay, right. Now that we have all the parameters and relations set, the start of this build is the same as the straight bevel gear system. We're going to be starting with this sketch here. Okay, so we're going to sketch on the front plane, orientate our view. We're going to be putting a center line on the x-axis because I want a rotational axis for later. You can either do it in here with the center line, it will just automatically create that axis. You can do it in the main model by creating an actual axis from the datum plane, the datum tab up here, but this is just, this is fine. So, line up here. Yeah, let's divide there. Line here. Okay. This is obviously the cone distance line. These two lines here are at right angles to this line here. And we're going to set this angle, which is going to be delta 1, this length here, and this length here, which is the face width. Okay, right, so now we go into Tools, Relations, and again, you might have different values here for, it might be SD1, SD2, SD3. It depends what modeling you've already been doing that day. It doesn't matter just so long as you relate the correct values to each of these dimensions. So let's start with SD3. This is gear 1, so we want this to be delta 1. Insert to relations. SD6 is going to equal to the face width. Insert to relations. In this instance, you're going to use either of these. Okay, SD5 is going to equal to R, which is the cone distance line. Okay, verify that and press OK. Excellent. Right, let's move some of these just out the way slightly. Bring you back in. Next up, the root and tip need to be brought in. So let's extend these lines arbitrarily. I'm going to divide here and here in random positions and just draw this in randomly as well and delete these two. Okay, next up, I want to have this angle defined, this angle defined, this addendum defined, and this addendum defined. So let's do the addendums first and the addendums first. So tools, back to relations, enter. The addendum is HA, the addendum is HF. So we want to find HA1, which is 3.4275, insert to relations, and press OK and verify that. Okay, and the addendum is going to equal HF1. Okay. Remember, typically this would be the addendum is 1 times the module, which it would be 3, and the addendum is 1.25 times the module, which would then be 3.75. Whereas in this case, the addendum is smaller than the addendum. Just to keep note of these, and it's the opposite value for gear 2. But when you put the two gears together, the clearance on both gears is exactly identical. You can see that by here. The clearance for both is calculated as 0.564 and 0.564 for both. Okay, next up, we want to put in the root angle and the tip angle. So where are these? All right, so SD19 is the tip, so that equals 29 something, and the root equals root angle 1. Make sure you are choosing the correct values. Make sure you're choosing root angle 1 for gear 1, root angle 2 for gear 2, and so on. Otherwise, you'll have a very frustrating time down the line when nothing works for you. Verify, and press OK. Okay, so this is where the build order between straight bevel gears and spiral bevel gears begins to diverge. Next up, we want to create a revolve and a surface revolve at that. And what I want us to do is I want to do this on the front plane. I'm going to project this line here, which is the same line as the cone distance line, which can also be referred to as, this point here. It's the pitch circle or the reference circle. So let's do that. Let's press OK, and let's press OK, and we're going to revolve that against here. Okay, so we have this surface generated, which is the cone of this gear. We're going to be using this surface to project the curve that is going to be the trajectory of the spiral tooth, okay? Which we'll then use for a swept blend. Now, the sketch for this, if I just go into the calculator and let's go to look at sketch reference gear 1, notice that for sketch reference gear 1, we're looking at the side of the gear here, whereas for sketch reference gear 2, we're looking top down for the sketch. Very important, and it's very important to get this right when building this out. Also, very important to get right is that notice that the orientation is opposite to each other between the gear 1 and gear 2 spiral cuts here. So this is with a this sort of spiral angle towards the left. This is with that same spiral angle to the right. And that is because these curves are going to be produced in the opposite direction to each other so that they actually can merge together and mesh together effectively. So we are on gear 1, which means we're going to be putting this sketch in from the side. So what I want to do, let's see here, I think it's this orientation. Yeah, okay. So I'm going to sketch on the top plane, sketch, orientate the view. Let's reference here, 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 okay. And the first thing we're going to do, we want to build up this sketch systematically. First off, I'm going to draw a line intersecting this cone. I'm going to drop a point at the center of this line. Next up, let's have a look. Yes, to the left. I'm going to draw another line connected from the top of the cone through this point to the base of this cone. There. Now I'll set this angle. Tools, relations, SD1 is equal to the mean spiral angle, insert relations, verify, press OK. Back to sketch. Yeah, next up, I'm going to extend from the middle here another line, perpendicular, just into space, and create a circle that originates from the end of this line to again intersect with this point here. Okay, this distance, back to tools, relations, SE3 is going to equal, I think it's towards the bottom actually, is the cutter radius. Insert to relations, verify, press OK. All right, we're nearly there. Next up, line. This is going to connect from the center of the circle to the base here. And then again, I'm going to put this into space somewhere along here. Arbitrary, I don't want to snap to anything, just arbitrary for the moment. All right, and I want to dimension the angle between the two newly created lines. And this is going to be set to tools, relations. We'll be in and out of this a lot, as you can see. SD5 is equal to the cut path angle. And insert relations, press OK, and press OK. Now, before we accept this, we want to use the divide tool to divide here and divide here. Select this larger slice of the circle and change you, reselect, change you to construction line. This, 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 and this line are also going to be turned into construction so that we are left with a single arc here, which is going to be the trajectory of our teeth. Press OK. Excellent stuff. Now, we want to project this line onto this cone, but this cone is not large enough for the teeth geometry we want, and will not create a tooth correctly, not without a lot more intervention from us, which none of us have time for already. So let's extend this cone by clicking the top edge of both halves of this cone, press extend. I'm going to extend this out. Doesn't really matter what the value is, just so long as, let's go to the top view, just so long as it extends above this line here. Press OK. Brilliant. It means now that we can go back to this sketch, press project, and click on this cone. And now we have a curve in the same plane or curved plane as the pitch circle here. Fantastic. All right. Now, to make things easier, what I would like to be able to do is reposition this curve or copy this curve so that this point that intersects with the base of this cone intersects also with the pitch circle point here. To do that, what I'm going to do is go back into Sketch. I'm going to sketch now on the, what plane is this? The right plane. Press Sketch. Orientate my view. I want to reference this, reference that point. Okay. Center line through there, center line through the top. And I just want to calculate or just see what this angle is. 17.81. Make note of that angle, please. Cancel out of that. Go to the projection, pattern along the axis, choose this rotational axis here, input 17.81 to, is that the right direction? No, there we go. Press OK. Oh, no, it was the right direction. Let's go back into there, flip, OK. There we go. And now we have our copy of that projected line exactly where we need it to be for when we actually create the profile of the teeth later in this model. All right, so we have our trajectory for our teeth. If I want, I can now hide this revolve. Next up, I'll keep it for the moment just for a bit of reference. Next up, similar now again to how we created the straight bevel gear, I want to create a series of circles here, these ones, which means we need to create a coordinate system down here. To start with that, I'm just going to put a point at the end. I'm going to create an axis, connect to that point, and cutting through the front plane here. Press OK. Next up, let's drop in a coordinate system at the base here. Go to orientation. I want it to be orientated along this line here. And I want this to be, what was it? Off the top of my head, I think it's Y. And I want this axis to be used. And I think I want this to be X. Yes, I'm pretty sure that's right. Okay. Oh, if it's wrong, we can change it later, and we'll see that when we put the involute curve in. Okay, next up, a plane here and here. Set that to 0. No, was that wrong? Set that to 90. Aha, it was 90. Okay, press OK. And we're going to sketch on the newly created plane. We're going to create some references here at the end and here. Okay, reorientate the view, zoom out a bit. Now let's hide that revolve. And from the center of the new, where we created this new coordinate system, we're going to extend 3 circles that snap as such. Okay. So tip circle, pitch circle, root circle, I believe, not base circle. Right. Next up, we are going to bring in the involute. So let's go to datum. curve, curve from equation, choose the coordinate system, edit, and we are going to go back to our calculator, back to the relations tab, and gear 1, not gear 2, gear 1, curve, involute curve equation. Control C. The only difference here is that one references D1, one references D2. So you could copy this in, but you just have to make sure you change D2 to D1 and vice versa. Okay. Control V and press OK. And that was in the right direction. Excellent. Okay. I was referring to my orientation of the coordinate system there. It's perfect. Okay. Let's create the tooth profile. Well, actually, first, let's trim this because it's just too long. So click that, trim, trimming object is U, flip that round because we want to get rid of this blue highlighted section and press OK. Now we have a nice involute tooth profile right here. Okay, sketch, back on this plane, orientate our view. Let's reference each of these circles. Let's reference U, and press OK. Let's project U, and press OK, projecting the involute curve there. I'm actually going to hide these curves at the moment because otherwise they're just going to get in the way. And let's also stop looking at these coordinate systems there for a minute. There we go, that's a bit nicer. All right, we're going to create an arc along this pitch circle. We're going to dimension that arc, and we're going to, remember dimensioning an arc, you need to select one end, then hold Control, select the other end, select the middle of the actual line of the arc, and then press the middle mouse button to put the dimension out there. We're going to relate this, and we're going to use normal tooth thickness. Insert, verify, and press OK. Next up, back to the sketch tab, a point in the middle, a center line from that point here, and we're going to mirror the projected involute curve across that, and we're going to change this arc to a construction mode arc. Let's cap the end there, and then what we're going to do is we're going to bring this down to the center of this circle there. Right, that's a completed section, but I don't want all of this. So what I'm going to do is line this up, and I want this to be parallel, this line to be parallel to this line here. Delete these. Yep, those lines equal to each other. I want to extend this out to, let's say, 8. Okay, press OK. Okay, we have a sketch of our teeth profile. Now, however, if I bring our second projection back in, you'll notice that obviously this tooth profile does not line up with this projection, this trajectory line that we have here. I could have gone to many lengths within this sketch to use our involute curve to orientate and position this in here, but frankly, it's far more complicated to try and reposition this profile in this sketch to the exact position of here than it is to simply find the angle here, 4.88, keep note of that. Get out of that sketch, select the sketch, and pattern that sketch across the rotational angle of the actual gear itself. Going the other direction this time, we only want 2, and the value is 4.88. And press OK. Now I can hide the first sketch, and I have my perfect tooth geometry profile exactly where it needs to be. Oh, exactly where it needs to be? No, it's not. Why did you not go exactly to the right position? Let me go back into the first sketch, orientate the view. .88. Oh, okay. I think I understand. It's because I actually need to use, let's review, the axis is actually this z-axis here. Yeah, there we go. Yeah, I used the wrong rotational axis. It was the rotational axis of this circle here, this coordinate system, not this one here. That was the error. Okay, good. That was going to confuse me for a while there. Excellent. Now, as you can see, that's perfectly in line our second profile. So I can go back and see that everything lines up as it should. The next stage is to actually create that teeth geometry. So what we're going to be doing is we're going to be creating a swept blend, choose that trajectory, make sure it's orientated in the right direction to be starting from here. It's going to be a constant normal direction using this plane as the reference. And once we've selected constant normal direction in this section plane control section here, we go to the sections tab, define the sketch, and we're just going to project this tooth profile into existence. Okay, we're then going to insert, sketch, and just put a point, and press OK. And as you can see, we have our first tooth geometry created. Let's press OK. At this point, what I want to do is rotate this. So we're going to click that swept blend. We're going to pattern it. We're going to use an axis pattern. And now we use the rotational axis of the actual gear here. Angular extent, press OK. And we're going to go into Tools, Relations, go to the end, click on the pattern itself within the model tree, find the P that has the two lines connecting, or the lines connecting between the first and second patterns within the set, click on that, and that's going to equal Z1, which is the number of teeth in gear 1. Verify, and press OK. Nothing's happened yet because we need to regenerate, so let's just either click here or press Control G. All right. Now, doesn't that look rather gnarly? It doesn't look like teeth yet, really. So what we're going to do next is we're going to do a revolve to remove some material. So let's revolve on the, I think that's the front plane. Orientate our view. And now we want to reference, if we zoom in here, I want to reference this line here. Okay, orientate my view, and I want to extend this line up like this, press OK, and we're going to use this angle here, and we're going to remove material. And you'll see that everything on this side, you can flip that if you like, but everything on this side of this line rotating has been removed. Okay, great. So you can see we have our teeth geometry here. Okay, let's save that. Now we just need to create the actual body of this, this gear, and for that we're going to be using our original sketch as a reference. So if we go into a revolve again, use this plane as our reference, I'm going to use the project tool, and I'm going to project the root line here, this line, hold control, this line, and this line, and press OK. Let's just delete you. Okay. So next up, I'm going to draw another line going straight down to the axis. Arbitrarily, I'm going to do the same thing over here. I'm now going to delete this line and this line. And I want to dimension this. Let's set that to 15. Here, let's set you to 5. Close off the sketch. Press OK. Select the axis. And press OK. And like that, we have our pinion bevel gear. Okay. Now, I purposely started by using 55 as, I think it's in this sketch here, 55 as the cutter angle here. Now, in a straight bevel gear system, the trajectory of the tooth that we create, if I exit out of this, you'll note that it actually is the entire length of this line going to 0, meeting at 0 exactly as its counterpart gear also extends to 0 at the end of this line. For this curve, that isn't possible. So the cutter angle, we've set it to 55, and I've actually set some parameters within the calculator to help calculate this angle here, which is just 90 minus the mean spiral angle. But that's kind of a rule of thumb when it comes to this. Obviously, the actual spiral angle itself is important. But one thing I've noticed when I built this model originally is that with the this trajectory being quite short, as you know, the tooth profile is via swept blend sweeping into nothing. And I do think actually that just slightly the end of these teeth are quite small. So what I'm going to do is go back into the sketch, not this sketch. Wait, hang on, was it that sketch? Yes, it was that sketch. Orientate my view. I want this to be left. No, I don't. I want it to be front. No, I don't. Orientate my view. Because that would be left would be for the gear 2. That's why I was using left. Okay. I'm going to change this. Go into tools, go into relations. This cut path angle, SD5. I'm actually just going to delete that. Verify. Okay. I'm going to re-put in SD5. And I have that equal 65. And accept that there. Control G. Okay. Yeah, that's a bit better for me. And now just the profile at the end of these teeth are just ever so slightly larger at the end of this particular bevel. Let's save that there. Okay, so that concludes the build of the pinion gear. Now, unlike with the straight bevel gear, where we could copy, you could save this as a new model and go straight in and just build it again. Because of the complexity, we're actually going to be we're going to be starting again effectively. So let's jump straight in. And there's a key difference for that as well, which is after the revolve, which is very early on, the reference sketch that creates the geometry for the trajectory of the tooth profile, they're on two different planes, and they're needed to be so, which is why just copy and pasting in this instance doesn't work so well. So